Okay, welcome back. In this video, we're going to talk about nuclear reactions. There's two types of nuclear reactions, and we're going to explain them in detail and talk about some of the real-world applications to those nuclear reactions. So I think it's very interesting stuff, and hopefully you will think it's interesting as well, and you will understand it by the time we're done. So, okay, let's get started. The first nuclear reaction that we're going to learn about is called fission. Fission. You're supposed to write it, so if you're watching the video, please have your guided notes open and be filling out your guided notes as we go through this. So fission is the splitting of a large atom into two smaller atoms. Okay. So it is the splitting of a large atom into two smaller ones. So we're taking something, a large atom on the periodic table, a large atom, and after the fission reaction takes place, we got two smaller atoms. Okay? So we're splitting it and making two smaller ones. Okay, let's contrast that to the other type of nuclear reaction called fusion. Fusion, like it says here, is the fusing of two smaller atoms into a larger atom. So this is kind of the opposite of fission. We're taking two smaller atoms, and fusion reaction takes place, and it makes one larger atom. See how they're kind of mirror images or inverses or the opposites of each other? So fission is the splitting, fusion is the fusing of two atoms together. Okay, so we're going to talk about them in more detail in the coming slides. Here's a good animation of what fission is. Okay, it's going to go through, it's on a loop, so we'll watch it a few times. Now you see a few things happening here that's noteworthy. First is, what is this little blue dot that comes through right there? What is that? Well, that is a particle. What particle would you shoot at an atom to get it to split? Would you shoot a proton, a neutron, or an electron? If you were going to do it. Knowing their charges, which one would you shoot at it? Well, proton you could, but then wouldn't it hit the positive nucleus and kind of maybe get deflected off? So which one should we do? Neutron. Yeah, neutron. What charge does a neutron have? It's neutral, so it's 0. Okay, so what this blue dot coming in right here, that's a neutron. And they get it going really fast and they shoot it at an atom. And what happened to that atom? It split. But then what do you notice coming off of the atoms? More what? More neutrons. Could those neutrons then be used to split other atoms that are nearby? Absolutely. And that's exactly what happens. So fission is the splitting of a heavy nucleus into two nuclei with smaller mass numbers. So you take a large one here in the middle, like right here, and you make two smaller nuclei. So two smaller atoms. Okay, but then notice you still have more neutrons coming off of that. And so here's the real-world application of fission reactions. We can start with one atom, this uranium-235. If we hit it with a neutron really hard, really fast, we can split it into two smaller atoms. But then notice, more neutrons are coming off. And so these other radioactive atoms that may be nearby are also hit. And so it causes this chain reaction. It's kind of a snowball effect. And so all of these other ones are going to also split. And so fission reaction can start here, but it snowballs and it's like a chain reaction. And imagine how many uranium atoms we could fit into just even a small chunk. Even a small chunk like this big. How many atoms are in there? Trillions and trillions and trillions and trillions of atoms in something as small as that. And so if once you get it started, that chain reaction just goes through almost instantly, and that fission will happen to all of the surrounding atoms next to it. So that's a fission reaction. It releases a lot of energy. We're going to talk about the energy that's released here in just a second. Okay, let's talk about the real-world applications of fission reactions. Okay? Fission reactions occur in nuclear power plants. And also, that's how nuclear bombs work. So this right here, a nuclear power plant. We see this big dome structure. That's it's the top of the reactor. The reactor core is somewhere below ground underneath it. These big towers here, so this big tower and this big tower are just cooling towers. And so that's kind of the what a nuclear power plant looks like. And then obviously a nuclear weapon, a nuclear bomb, is detonated and it releases a lot of energy. So, fission reactions. What do you guys remember from fission? Tell me what it is. Dallas.
It's when they split apart, like the atom.
So one atom splits into two smaller ones. Good. So on the periodic table, if you're watching the video, if you look at your periodic table, look at the bottom of the periodic table. This is where all the large atoms are, right? So we're taking something down here and splitting it with a neutron, and you create two smaller atoms, two elements that are above that in the periodic table. So you take one large atom and split it into two smaller ones. Okay, and that's what's happening. It releases a lot of energy. We can use it to harness power or electricity with a nuclear power plant. Or we can put it in a reaction, not even control it at all, make it happen really fast, and all that energy is released at one time. And that's what a nuclear bomb does. Okay, commonly used elements in fission reactions are large ones. So uranium, how many protons does it have? 92 protons. So its atomic number is 92. And plutonium, okay, another large element next to it. Okay. All right, let's diagram, go into the kind of schematics of a nuclear power plant. I want you guys to be able to understand how it works. Okay, we're going to start right here. You remember that big dome building that I kind of outlined earlier? Well, this is the dome. This is the reactor part. Okay, so the reactor core. Let's just start there. The reactor core right here contains these control rods. Control rods have the nuclear material in it, the nuclear isotopes, whether it's uranium, whether it's plutonium. You can use a lot of different types. It's usually a very large isotope, though. Okay? And that's where the fission is taking place. It's underwater. They can control it by lifting the control rods up and down out of the water. They can slow it down or make it go faster, make it really hot. Okay? And so notice that there's water surrounding it. Okay? Well, the water heats up. These nuclear reactions, fission reactions, releasing a lot of heat. So it heats the water up. When you heat water up, what happens to it?
Evaporates, makes steam.
Yeah, it makes steam. And what happens to steam? Well, it rises. Okay? It rises, and the steam comes over here, and it goes through a what?
Turbine.
A turbine. That turbine is spinning. Okay, and it's producing what kind of energy? Electric energy. So it's producing electricity. And that's what's taken off, and the power lines take it off into your houses, right? Or to here at the school. Yeah. Well, then you got to cool it. After it comes through there, you cool it back down in this condenser. And so it cools it back down, and then it kind of just cycles back through. A nuclear power plant's always got to be next to a water source, whether it's a river, it would have to be a pretty large river, a lake, or an ocean. Because you've got to have water coming in to cool down the reactor. This is going to be cool water, kind of cool it down and keep it from getting too hot. If it gets too hot, then it just blows up. Okay? And so usually we've got some pumps here that are pumping the water from the river, lake, or ocean. And then you've got an outlet for that warm water to get back into the water source as well. If you remember, it was about, 5 or 6 years ago, maybe 7 years now, the nuclear meltdown in Japan, Fukushima. What caused that? You guys remember? So there was an earthquake off the coast of Japan. But the earthquake didn't really hurt the nuclear power plant. What happened? The tsunami. Yeah, it caused a tsunami. And because these nuclear power plants have to be next to a water source, that one was next to the ocean. The tsunami came, the waves come through, it knocked out the power to the pumps. So now there was no way for them to get cool water into the reactor core. If you remember, I'll show you a video later. They were actually trying to use helicopters with big buckets, picking up water from the ocean and trying to just dump it on top of the reactor to cool it down. Because it wasn't getting any cool water in here, so it's just getting hotter and hotter and hotter. And eventually what happened? Yeah, that didn't work. So it just got to a point where the temperature was too high and it blew up, okay? The whole reactor core just blew sky high. And why is that a bad thing? Well, you've got radioactive isotopes in here. Where do they go? They go into the air. And then it's just up to the weather pattern at the time to take it wherever it's going to go. They actually detected radioactive isotopes in New York City a few days later. So all the way from Fukushima, Japan, all the way across the Pacific, all the way across the United States, and they detected them in New York. And so these radioactive isotopes are very, they produce radiation, alpha, beta, gamma. Dangerous? Of course it's dangerous. Nobody lives around Fukushima's nuclear reactor today. Nobody ever will live real close to it. So they call it a hot spot, so it's very unsafe. Anyway, that's kind of how a nuclear reactor works, nuclear power plant. Now, we live next to IPP, a coal power plant. What's the only difference between IPP and this?
Use coal.
Yeah, it's the source that we're using to heat water. What do they use at IPP? Coal. After that, it's all the same. The steam comes up, turns the turbine here, and everything's the same, except for how they heat the water. I guess there is some differences. What are the trade-offs to IPP? It releases, when you burn coal, what do you release? Carbon dioxide is one of them, but other pollutants as well. So you release pollution into the air. That's a trade-off. We get energy from it, which is great. What's the trade-off with a nuclear power plant? Do these control rods last forever? Nope. And you've got to store them somewhere. You take the old ones out, and you've got to store it somewhere. How long does this stuff last? What's the half-life of most of these things?
A long time.
Long time. Okay. So you've got to find a place to store this nuclear material basically forever. And that's very difficult to do. So there's trade-offs both ways. But anyway, that's how they work. Any questions with the nuclear reactor there? Okay, now let's talk about fusion in more detail. So that was fission. We split a large atom into two smaller ones. Now we're going to talk about fusion. Okay, this is a fusion reaction. This diagram here, this is showing us, watch here, two small atoms coming together, and they're going to fuse and make a larger atom. Let's watch it a few times. How many protons do the atoms have that are coming here? How many protons there and there? 1 and 1. So what element is it? You look at the periodic table, which one has 1 proton? Hydrogen. So what they're doing is using two small atoms, two hydrogen atoms, and they're fusing them together. They have to come together at extremely high speeds. They smash together, and it fuses to make what element there? Helium. Well, here's an easy way of determining that. How many protons does hydrogen have? 1. What's 1 plus 1, guys? 2. So if you fuse two hydrogen atoms together, you make helium. Okay, so fusion is the combining of two light nuclei to form a heavier, more stable nucleus. Now, fusion releases a lot of energy as well, actually a lot more than fission. So let's talk about where these reactions occur. So, this is another diagram. So you have hydrogen here, you smash it into another hydrogen here, they smash together and it makes helium. One proton right there, one proton right here makes two protons, helium. And releases a lot of energy. Okay? It releases a lot of energy. And it also releases a neutron, which, 1, 2, 3, actually no. So it can do a chain reaction as well. Fusion reactions, let's look at where they occur. Fusion reactions are occurring in stars. So they occur in stars. Our sun is burning as a result of hydrogen atoms fusing together to make helium atoms. So on the surface, or our sun right here, that's how it's burning. That's how it's so hot. It's not burning from like burning coal or something's on fire. It's burning because hydrogen atoms are coming together and making helium atoms through nuclear fusion reactions. Okay, here's a good diagram that shows the amount of energy that's released. So the energy released. Let's look at it. So let's talk about a chemical reaction first. This is like IPP right here. So let me write that in. IPP. It's burning coal, which is a chemical reaction. It's combustion. Okay, we take coal and we burn it. And I want to focus on this part of the table, which is the amount of energy released. It's measuring in terms of joules per kilogram of material, but that's not important. I want you to notice the order of magnitude here. 3.3 times 10 to the 7. Okay, let's just compare that to the next one over, which is fission. This is a nuclear power plant. For 1 kilogram of material, it's releasing 2.1 times 10 to the 12 joules. How many times greater is 10 to the 12 than 10 to the 7? So every one of those, is that 5 orders of magnitude? So if we have, here's how you determine that. Let's move it 5 times over. 1, 2, 3, 4, 5. Okay? That's 100,000 times more energy per kilogram of material. So of course, nuclear power plants can release a lot of energy per kilogram of material. Okay, now let's compare that to fusion. Where are fusion reactions occurring, guys? Where at? Stars. Our sun. This is what's happening with our sun. How many orders of magnitude? 10 to the 14th. How many times more energy is released with fusion than with fission? So move it over 2 times. 1, 2. That's 100 times more powerful than fission. So in fusion, a lot of energy is released. Fusion. Okay, then why don't we have fusion reactors? Why don't we have fusion power plants? Does anybody see something on this slide that would tell you why we don't have fusion power plants? The temperature. Yeah, look at the temperature. You burn coal, 700 degrees Kelvin. Fission, 1000 degrees Kelvin. Look at this one though. 100 million degrees Kelvin. That's really hot. Are there any materials that we could build that power plant out of to withstand those temperatures? No. Basically, it would melt everything. You couldn't contain it. There's no way we could control that reaction. And so that's why there's never been a nuclear fusion power plant. Now, can we still do those reactions? Sure. But can we control it? No. And so they're working on, at least they were, I don't know, cold fusion. Have you heard of that? Cold fusion is where they're able to fuse two atoms together at a much lower temperature. But it's never been done. It's kind of just a thought right now. So anyway, that's why there's no fusion power plants. But it does work. I mean, that's how the sun is burning. All the stars that you see at night are burning with fusion reactions. Okay. So here's a good question. Why are they so powerful? Why are these reactions so powerful? Nuclear reactions are way more powerful than chemical reactions. Why? Well, in nuclear reactions, some of the mass, this is where you should pay attention because this is where it's going to get a little more complex. In nuclear reactions, some of the mass of the atom is converted into energy to help hold the nucleus together. Read that again. In nuclear reactions, some of the mass of the atom is converted into energy to help hold the nucleus together. That doesn't really make sense, does it? Well, Albert Einstein, that's why he's one of the reasons he became so famous, was able to calculate the amount of energy produced in those reactions with this famous equation, E equals mc squared. Okay, you're going to have to know this equation for the test. E equals mc squared. You see it all the time with Einstein's picture, right? You've heard of this equation? It's one of the most well-known equations in science. Well, nobody had figured it out before. That energy can be converted into what, guys? What does the M stand for? Mass. Energy can be converted into mass. And vice versa. Mass can be converted into energy. Isn't that crazy? We can get something with mass just from energy. So we can get something from basically nothing, right? Does that seem crazy to you guys? Okay, let's talk about what these variables mean. What is E for? Energy. Do you have to write that? Let's see. Yeah. Okay, so energy is equal to, what's the M? Mass. The mass defect is what it's actually called, mass defect. And what does C stand for? The speed of light. But what do you notice about the speed of light? It's being what? Squared. Is the speed of light a large number? Sure, it's the fastest speed anything can go. And then you square it on top of that, and so you're getting a very large number right there. So even though the mass defect might be very small, because this C squared number is so big, what kind of energies are we producing? Pretty big amounts of energy from very little mass. Okay, let me talk about mass defect for a second. So on that equation, E equals mc squared. The M right here is mass defect. What is a mass defect? Well, what it means is that the mass of an atom is less than the sum of its parts. That doesn't make sense, does it? If we take a helium atom, okay, helium, He. Guys, how many protons does helium have? Look at the periodic table. 2 protons. 2 protons. How many neutrons would it have? 2 neutrons. Well, we know the mass of a proton and a neutron. So if we take the 2 protons, times it by its mass in AMUs, we get this number. We take the 2 neutrons, times it by its mass in AMUs, we get this number. Then let's just throw in the electrons. Even though they have very little mass, It's got 2 electrons. So we times them together, it gets that. Well, it should have a mass of 4.032979 AMUs. That's what it should have. Okay? But what does the periodic table say the mass of helium is? 4.00260 AMUs. But we just added up all the parts here. How come it doesn't add up? How come the actual mass doesn't add up? That's what Einstein figured out. Part of the mass in making up the helium nucleus is converted into what, guys? Energy to help hold that nucleus together. It takes a lot of energy to bind all those protons together. They don't want to be by each other. So the mass lost during the formation of an atom was converted into energy to help hold the nucleus together. So when you destroy or when you split an atom or when you fuse it, that mass defect is then converted into energy. So E equals mc squared helps us determine how much energy is produced. So E equals mc squared says that mass can be converted into energy when the nucleus is formed or changed. So let's read this last couple bullet points. In nuclear reactions, large amounts of energy are released when the nucleus changes. Energy is so large because the speed of light is a huge number. Here's the speed of light. So it's 299,792,458 meters per second. But then when we square it, it's going to be a huge number. And then what we do, let's go back a slide. What would the mass defect be here? How would we calculate mass defect? I want you to get your calculators out. Okay? Get your calculator. Type in this number. This is what the helium atom should weigh. Okay? So let's type that in. 4.032979. And I want you to subtract off what it actually weighs. So subtract and then put in this number. 4.0026. What do you guys get? 0.03? Did you guys get that? 0.03. This number is called the mass defect. That's the difference between what the atom should weigh, or it should have the mass of, compared to what it actually has the mass of. So remember that number, 0.03. Now when we put it into this equation, energy is equal to the mass defect, 0.03. Let's do this. What's the speed of light? Well, it's this big number, 299,792,458. But you got to square that number. So times it by it, do parentheses, 299,792,458 parentheses squared. And I get some huge, gigantic number of 2.73 times 10 to the 15th for the energy. Huge amount of energy coming from very little mass. Why again? Because you're timesing it by the speed of light squared. So even though your mass defect is very small, the energy produced is very large. And so we can produce large amounts of energy from very small amounts of mass. This is incredible. When Einstein was able to come up with this equation, it explained a lot. Look at it. Energy is equal to mc squared. We can get mass from energy and vice versa. So we're going to talk about the Big Bang next class period. The Big Bang is a theory where there was this whole bunch of energy at the beginning, and then it all kind of converged at a single point and created all the mass that we see in the universe. All the matter that's here was converted from energy. And so this equation is very famous, but going from energy to mass and vice versa was explained by Albert Einstein. Anyway, well, hopefully that helps, kind of helps you understand the differences between fission reaction and fusion reactions. All right, before I stop the video, I wanted to review with you a little bit. Which one takes a large atom and splits it into two smaller ones? Fission. Which one takes two smaller and combines them into one single large atom? Fusion. Which one releases more energy? Fusion. Okay, where do you see, let's go back to fission. Where do you see fission reactions happening today? Nuclear power plants and nuclear weapons, okay? Nuclear power plants are fission reactions, and nuclear weapons. Where do you see fusion reactions happening today? Stars. Our sun is burning by fusion reactions. Okay, good job. So hopefully that gives you a little bit better understanding of nuclear reactions and how they work.